In today's video, we're going to discuss the periodic table and relevant trends that you should know for the MCAT. The periodic table was initially created by a Russian scientist by the name of Dmitry Mendeleev, and he was able to figure out a few of the trends that occurred with the different elements on the periodic table by which we can classify them and show a useful categorization or organized version of them. The first place let's start from is how we define the rows and columns on the periodic table. So the rows on the periodic table are known as the periods and go from left to right, and they will designate the principal quantum number that is present in the naturally occurring and synthetically created elements. If you want more information on quantum numbers and what the principal quantum number represents, please watch my video on electron configurations and quantum numbers. The groups on the periodic table represent the columns, top to bottom. And so in each group or column, the numbering is going to give us information about how many valence electrons we can expect in the valence shell of each of these elements. The valence shell is the furthest distance away from the nucleus and contains the valence electrons, and those have the highest energy in the atom. Groups 1 and 2 are very straightforward because those are the number of valence electrons we can expect. Group 1 is known as the alkali metals. Group 2 is known as the alkaline earth metals. We will see this in a second. Between groups 3 and 12, we have our transition metals. The transition metals tend to have very interesting chemical properties where they can form multiple different ionic charges. So we're going to leave them out for now. They don't follow the guideline that I'm trying to give you here with the group numbering. But if you continue from 13 all the way to 18, the second number, 3, 4, 5, 6, 7, and 8, are going to represent the number of valence electrons we can find in those groups. Keep in mind that group 18 consists of our noble gases, which are inert. They don't really have a reason to react with anything because they are already stable. The reason they are stable is because they have 8 valence electrons in their valence shell, and that is known as the octet rule. Please refer to my video on valence electrons and the octet rule and Lewis dot structures for more information on that. On the left side of the periodic table, we can expect to find a majority of the metals. Once we go past group 13, you can notice that in between the metals and the non-metals, which everything to the right side of the table is more likely to be a non-metal, you'll find that there's a little staircase right here that contains what are known as our metalloids because they share metallic and non-metallic qualities. The first two groups or columns are located in the S block. So this means that their valence electrons are located in the S subshell. The transition metals, as we said earlier, have their valence electrons in their D subshell. But what's interesting is that they have the possibility to lose from the S orbital before they lose from the D subshell. And so that makes them far more tricky to predict. Once we hit group 13 and onward, besides helium, then we're going to be within the P block, and you can expect the highest energy valence electrons to be located in the P subshell. Hydrogen and helium are interesting exceptions because hydrogen is a nonmetal, even though it's in a group with a bunch of other alkali metals. And the reason it's a nonmetal is because it already has a half-filled valence shell, which is just its 1s orbital, which has one electron in it. So if it gains one more electron, it becomes a noble gas, and that is going to be helium. So helium's electron configuration would look like this. Every other element below hydrogen and helium is expected to meet and respect the octet rule, where the valence shell should include 8 electrons. Because this table doesn't include the F block, I just want to make it clear that the electrons within the actinides and the lanthanides are going to be considered the F block. And if you go to Chicago, you can see the O block. No, I'm just kidding. Let's move on. So I'd like to go over a very important idea here, which is key to understanding the periodic trends that we're going to discuss after this point, and it's called effective nuclear charge. So this formula here shows us that the effective nuclear charge, which is written as Z effective, is equal to the nuclear charge, which is the number of protons in the nucleus, which is also known as the atomic number, subtracted by the shielding electrons will give you the effective nuclear charge. And so the question is, what are considered these shielding electrons? So if we dive deeper into this diagram that we have here, I want you to notice that the nucleus is this collection of spheres in the middle and contains our positively charged protons. The electrons that are within the valence shell will be in the outermost highest energy level, and we'll call that this blue shell here. And the electrons that are in the core are designated by this green shell. And so if our electron of interest is this one right here, forgive the typo, I did not create this diagram, then the shielding electrons that we should consider, which are going to affect the effective nuclear charge of the nucleus on this electron, which is an attractive force from positively charged protons to the negatively charged electron. So the core electrons, or the electrons between the electron of interest and the nucleus, cancels some of the positive nuclear charge. So let's take that concept and roll with it. In this figure, you'll see a representation of the atomic radii that you can expect for each atom. Remember that atoms and ions are not the same thing. When an element is in its atomic state, you can expect that the number of protons is equal to the number of electrons, which means that atoms are neutral and in the ground state, unlike ions, which always have a charge. We will get to ionic radius in a moment. For the time being, I want you to notice what the general trend of the atomic radii is. If you look carefully, you can see that the smallest atomic radii happen to be up and to the right, whereas the largest atomic radii happen to be in the bottom left. So this means our atomic radius increases as we go down and to the left. And I'd like for you to take a moment to think why that might be the case. You would normally expect that the more protons and electrons something has, the bigger it should be, right? But if you think in terms of effective nuclear charge, as we had said earlier, the valence electrons do not have the same influence that the core electrons do within each atom. So if we take fluorine as an example, fluorine will have 2 core electrons and 7 valence electrons. And since the other valence electrons are not going to influence the effective nuclear charge, then that means that the 9 protons in the nucleus of fluorine will have a very strong pull on the valence electrons that it possesses. This is also the reason why fluorine has the highest electronegativity. Before we move to the bottom left of the table, let me show you how that trend persists across the period or the row. If we move to the left and we notice lithium, which is actually a very small element, very small atom, only has 3 protons and 3 electrons in the ground state, well, it happens to be bigger than fluorine. And if we draw out the statistics the same way we did for fluorine, lithium has 2 core electrons and 1 valence electron. So if we were to do the calculation that we did before for lithium, the effective nuclear charge would total 3, which is the nuclear charge positively because it has 3 protons, minus the 2 core electrons, which are in the way and shielding the valence electron from the nucleus. So therefore, the effective nuclear charge is equal to 1 for lithium. If we go back a second and we do that same calculation for fluorine, now the nuclear charge is going to go up to 9 because fluorine has an atomic number of 9, meaning it has 9 protons, and the effective nuclear charge is now 7. which means that the pull that fluorine has on its valence electrons is far greater than the pull that lithium does. And the tighter that the nucleus of fluorine can pull on its valence electrons, the smaller its atomic radius will be. The depictions above at the top are showing us how we can determine atomic radii when they're in the bimolecular state. Then by dividing by 2, you can determine what the atomic radius is. So the atomic radius gets smaller as you go from left to right and larger as you go from right to left. Very intuitively speaking, the radius also increases as you go down a group because there are more energy levels, there are more electrons. And so the space that they take up increases the size of the radius. If we move on to ionic radii, I don't have a diagram or a table to show the trend with this because it follows a slightly different pattern than the atomic radius does. But what is always true is that the radii of cations is always going to be smaller than what the parent atom was in the ground state. So for aluminum, you can clearly see that the ionic radius is significantly smaller than the atomic radius was. And the reason is because it lost 3 valence electrons, and therefore the pull that the nuclear charge will have, which is positive, is stronger on the core electrons and decreases the ionic radius in comparison to the ground state. For sulfur turning into sulfide, you can see that the opposite took place, where the ionic radius is significantly larger than the original parent atom, and this is because it's gained 2 electrons, which are added to the valence shell, which are going to experience a weakened effective nuclear charge, and those electrons are repelling each other because of electron repulsion and take up a larger radius around the ionic nucleus. So cations will always be smaller than the parent atom, and anions will always be larger than the parent atom. Just to make something clear, I'm going to go back up to this table, and I want to make a point about the ionic radii of isoelectronic ions. And all that means is that 2 ions have the same number of electrons. So for example, if we were to compare the fluoride anion to the ionic radius of the magnesium cation, which one is larger? So the fluoride anion would gain 1 electron and it would be isoelectronic to neon, meaning that it has 10 electrons. Magnesium also would lose 2 electrons and would go backwards isoelectronically to neon as well. However, which one has more protons? If you compare the effective nuclear charge here and you were to do the calculation, you would see that the effective nuclear charge of magnesium is clearly higher because it has more positively charged protons in its nucleus and it has fewer electrons in comparison. So the pull of 12 positive charges on 10 negative charges is going to be stronger than the pull of 9 positive charges on 10 negative charges. The positive charges are outnumbered in the case of fluoride, and therefore fluoride will have a larger ionic radius than magnesium 2 plus will. And so whenever 2 ions are isoelectronic, whichever one has a higher proton count or higher atomic number, given that they have the same number of electrons, will have the higher effective nuclear charge, and therefore will be the smaller in radius. So since I briefly introduced it before, we'll talk about electronegativity in more clarity right now. Based on our conversation about effective nuclear charge, you can see here that the highest electronegativity is in the top right, belonging to fluorine, and the second highest will be oxygen, and the third highest we'll consider to be nitrogen. Although the numbers seem very similar for chlorine and nitrogen, and they both have high electronegativity, we're going to say it's nitrogen for the sake of the test. In the bottom left, cesium and francium have the lowest electronegativity values. So this means that electronegativity increases as we move from the bottom left to the top right. Francium is unable to have a strong pull on its outermost electrons because it has 7 different energy levels of electron shells, and the ones that are furthest away are so far away from the nucleus and have so much repulsion from the other electrons in between the nucleus and the valence electrons. This means that it does not have a lot of electronegativity or pull on the electrons that it possesses. As we move up each group, you'll notice that the electronegativity values are increasing. The reason for this is because the valence electrons are simply closer to the nucleus and have less electrons in between them. Therefore, the pull on those valence electrons within that shell will be the strongest, as we saw with effective nuclear charge. That increases as you go up a group. The difference in electronegativity values between two atoms, so let's say between carbon and oxygen, if they were to form a bond with one another, will tell us if there's a nonpolar, polar, or ionic bonding that you can expect between them, because the electron cloud density will lean towards one way or the other. And in this case, we can say that the electron cloud density will be disproportionately on the oxygen side because it has a higher electronegativity. Carbon, on the other hand, will be considered the partially positive side. The arrow that I just drew is what's known as a dipole moment. For more details on that type of concept, please watch my video on intramolecular bonds. I want to clearly differentiate between electronegativity and electron affinity. Although they are very similar things, the definition of electron affinity is the amount of energy released when an atom gains an electron. So this follows a very similar trend to electronegativity. But remember that electronegativity is not measured in actual SI units or energy values. So electron affinity is measured in kilojoules per mole and tells us how much energy is released when an atom gains electrons. If an atom gains electrons and releases a lot of energy, that means that it decreased to a lower energy state, which is what essentially everything in the universe strives for and wants to do. It wants to achieve the lowest energy state possible. So if the atom loses a lot of energy from the results of gaining an electron, that means that it is stabilizing that atom and is likely to be a spontaneous process. We'll talk more about spontaneous processes when we get to thermodynamics. Nonetheless, the general trend for electron affinity follows the same pattern as electronegativity and increases as we move up and to the right. Please ignore the noble gases for the sake of electronegativity and electron affinity because they are already stable, they are inert gases, they have already achieved the octet rule according to their valence shells, and therefore do not really consider them as part of the trend for either of those. And last but not least, the opposite of electron affinity would be removing electrons from any given element. And to remove an electron, rather than giving off energy because one was gained, there needs to be an addition of energy. So if you want to dislodge the electrons from an atom, you need to apply energy. This table here is going to show us the first ionization energies. So that means the energy required to remove the first electron from any of these atoms. If you were to remove the second most valent electron, then you'd be looking at the second ionization energy. If it says the third, then that's the third electron being removed, so that's the third ionization energy. It will always be increasingly more difficult to ionize the second, and then it will be even more difficult to ionize the third, and so on and so forth, because you're moving closer and closer to the core electrons. So the closer an electron is to the core, the more difficult it is to remove, and the more energy is necessary to dislodge it. So if we look at the overall trend here, which group is it going to be the easiest to remove the first electron from? And it's clearly going to be group 1. Obviously, hydrogen is an exception to that because of reasons that we mentioned before. But if you look at the rest of them, lithium and moving downwards has the lowest ionization energy because the metallic character of those elements is higher as you go down the group. and it's the highest when we move to the left of the periodic table. Losing one electron is the easiest for cesium and francium because their valence electrons are the furthest away from the nucleus and have the least pull from the nucleus. That idea will come up over and over again. Also, they easily want to go towards the noble gas electron configurations, and by losing one electron, it increases their stability significantly as a cation. The higher you go in the group, so for example, compare lithium to cesium, the ionization energy is higher for lithium because those valence electrons are closer to the nucleus. If you look at the halogens, you'll notice that they have the second highest ionization energies in terms of group, but the highest will clearly be the noble gases, and this is mainly because the octet rule has been achieved and they are the most stable, so therefore they do not want to lose their electrons at all. I hope this was helpful with getting a better understanding of the periodic trends, and take care and see you soon.